When determining formulas, it is useful to write a chemical equation to think about the reaction. However, we often don't know what the product of our reaction is. We only know the masses of our reactants and products. So what can we do? We rely on two powerful and fundamental laws of chemistry. One is the law of definite composition, which states that composition of any chemical compound is constant, and the other law is the law of conservation of mass, which states mass cannot be created or destroyed, it just goes somewhere else. So we can assume that if we have some amount of product, and we know how much of one product was used, that we can figure out how much of the other reactant was used just by subtraction. So we can look at the equations on this page, and we see that the mass of one reactant plus the mass of another reactant is the mass of the product. Similarly, if you know how much product you made in a reaction, you can easily figure out how much of the second reactant you added just by subtracting the mass of the first reactant. Now let's practice. Suppose we have 0.175 grams of aluminum that was burned in the presence of oxygen to produce a compound that weighs 0.331 grams. And we want to figure out how much oxygen we made, and we also want to figure out a chemical formula for this compound that was produced in the reaction. So, the first step is we want to determine the mass of oxygen. So the mass of oxygen can be simply found by subtracting the mass of the compound and the mass of aluminum. So 0.331 grams total minus 0.175 grams corresponding to aluminum gives us 0.156 grams of oxygen, and that's the law of conservation in action. Now, let's find the moles. So we remember from experiment 2 that we can use the molar mass to convert from grams to moles. So first we want to convert moles of aluminum, and we can convert moles of aluminum from 0.175 grams to the number of moles using the molar mass, which is 26.98 grams per mole, and we get 0.00649 moles of aluminum. Now we can do the same thing with oxygen. We start with 0.156 grams of oxygen. We know that there are 16 grams per mole for oxygen, and then we can find that we get 0.00975 moles of oxygen. So now the third step is that we have to divide both those numbers of moles by the smallest number that they have in common. So in this case, you have fewer moles of aluminum, so you want to divide the moles of oxygen by the moles of aluminum. So we divide 0.00975 moles by 0.00649 moles of aluminum, and we get 1.50 moles of oxygen for every mole of aluminum. But we want whole numbers in a chemical formula. So if we multiply that whole thing by 2, we get 3 moles of oxygen for every 2 moles of aluminum. So we get our chemical formula, Al2O3. And this is what you're going to be doing in lab this week. When we write a chemical equation, we can use the mole ratios found in these chemical equations, aka the stoichiometry, to determine different quantities. So we can find out what the limiting reagent is in a certain reaction. We can also find out how much reactant is consumed in a reaction, i.e. how much reactant is needed for a reaction to go completely, and also we can calculate the theoretical yield of a reaction. If you need a review on any of these concepts, feel free to see Dr. Anderson's slides in the Content tab of D2L. Let's look at an example of how we can use stoichiometry to solve some practice problems. So for example, if we have 0.105 moles of propane that we burn in the presence of oxygen, how many moles of oxygen are consumed in the reaction? So the reaction we're looking at is propane C3H8 plus 5 moles of oxygen, which is O2, react to form 3 moles of CO2 plus 4 moles of H2O. So the question is asking us, if we have 0.105 moles of propane, how many moles of oxygen are we consuming? So what we need to do is use the mole ratios of both of these compounds. So we know that we have 0.105 moles of propane, and we know that for every 1 mole of propane that's consumed, we also consume 5 moles of O2. So if we do our canceling, we find that we have consumed 0.525 moles of O2 in this reaction. Now I want to solve another mole problem that's slightly more challenging. So in this example, we're reacting 2 moles of aluminum with 6 moles of HCl to produce 2 moles of AlCl3 and 3 moles of H2. If we start with 0.582 grams of aluminum, what is the theoretical yield of H2 generated in the reaction? And let's think about what is the theoretical yield of AlCl3 generated in the reaction. So the way that we're going to start this is we're going to use our mole ratios and the molar masses of each of these elements and compounds to figure out how much we generate in the reaction. So if we start with 0.582 grams of aluminum, we know that we first have to convert to moles of aluminum by using the molar mass. So 1 mole of aluminum contains 26.98 grams. We know that for every 2 moles of aluminum in the equation that are used, 3 moles of H2 are produced. And we also know that each mole of H2 contains 2.0158 grams. So carrying all the multiplication and division through, we see that we produce 0.0652 grams of H2. Now let's do the same thing, but using AlCl3. So if we start with 0.582 grams of aluminum, we know that we still have to use the molar mass of aluminum, so 26.98 grams per mole. We know that we produce 2 moles of AlCl3 for every 2 moles of aluminum used in the reaction, and we know that AlCl3 has a mass of 133.33 grams per mole. So carrying the multiplication and division through, we see that we generate 2.88 grams of AlCl3 in this reaction. So these are the types of questions that you're going to solve in this lab. So make sure you know how to do them, and if you need any extra practice, feel free to see me in office hours.